Hi everyone, my name is Giovanni Geraci. Welcome back to the fourth class of the course Signals and Systems 2 at Universitat Pompeu Fabra in Barcelona. If you have any questions on this class or any of the previous classes, feel free to get in touch via email with me, and you can also check my webpage for more information about me. In the previous class, we learned how to represent periodic signals with a Fourier series, which is a linear combination of complex exponentials. We also learned how to determine the coefficients of such series. Today, we will learn how to deal with signals that are not periodic. We'll do that by introducing the Fourier transform, which is an integral rather than a series. So let's get started. In this class, as I said, we will extend the concept of Fourier representation, which we introduce for periodic signals, to signals that do not possess this property, meaning signals that are not periodic. So to do that, let us think of a signal x of t as a periodic signal which has a period that goes to infinity. What do I mean by that? So let's look at the figure at the bottom right of this slide. The signal we're interested in is x of t. This signal extends between minus t1 and t1. It has finite duration, finite energy, right? Now what I'm trying to propose is to think of such signal x of t as a periodic version. So we just replicate the signal x of t and we create the signal x tilde of t, which is represented below. Is the same as the one above, but it's replicated. So this is a periodic signal, and in this case we are replicating it with period t. So at every t there's a new replica of the signal x of t, right? So of course we have the relationship that x of t is equal to x tilde of t over one period. So between minus half t and half t, which is the fundamental period, the two signals are equal, right? What I'm trying to say is that if you imagine this period t going to infinity, so if in x tilde you push the replicas away further and further apart, then you will end up ideally in the limit procedure with the signal x of t we're interested in. So now let's recall the Fourier series that we saw in the previous class. The signal x tilde of t is periodic, so we can represent the signal with a Fourier series as we already did. So the Fourier series is the sum over k of ak, which are the coefficients, times e jk omega 0 t. Remember that omega 0 is the fundamental frequency. It's defined as 2 pi over t, where t is the fundamental period. What about the coefficients? ak, these can be obtained with the formula 1 over t, the integral over one period of x tilde of t, which is the periodic signal, e minus jk omega 0 t dt. Right. If we further elaborate on this, we get that because x tilde of t is the same as x of t over one period, you have that relationship written at the bottom left of this slide. Well, then, because the integral runs from minus half t to half t, integrating x tilde or integrating x is the same. So we're just replacing x tilde with x. And once we do that, we can also replace the interval of integration with an interval that extends from minus infinity to plus infinity, because x of t has limited support. So we get the relationship written in this slide. Now, let us define x of j omega. X of j omega is defined as the integral of x of t, e minus j omega t dt. If we define such relationship, then we can rewrite the last expression from the previous slide in a more compact form. We can rewrite it as 1 over t x, capital X in this case, of jk omega 0. Right? Great. So now let's go one step further and everything will make sense. So now, because we have an expression for AK, which is the bottom row, well, we can substitute it back above in the expression for x theta. So now I'm substituting 1 over t x of jk omega 0 in place of AK. Okay, so I obtain the sum of 1 over t x of jk omega 0 e to jk omega 0 t. And this can be equivalently written in a different way by noticing the relationship between t and omega 0, right? So we always recall that omega 0 is 2 pi over the period. So here we just rewrote the expression in a different way. Great. So now we have come up with an expression for x tilde of t and an expression for the coefficients AK. But what we're interested in is a representation for the original signal x of t. X tilde of t was a periodic version of x of t that we artificially constructed. Right, but notice that as t goes to infinity, so as the period goes to infinity, as the replicas in x tilde get pushed away from one another, x tilde converges to x of t. Also, omega 0, the fundamental frequency, goes to 0 because it's inversely proportional to the period, and the sum that we have on this slide becomes an integral. Let's see that in formulas. So as I said, the sum converges now to an integral, and therefore we finally have an expression for our signal x of t. Our signal x of t, which is not periodic, can be written as 1 over 2 pi, the integral of x of j omega e j omega t d omega. Let's wrap everything up and formalize the Fourier transform and anti-transform pairs. So here we have grouped together the Fourier transform and anti-transform formulas. So x of t, which is the signal in time domain and it's not periodic, can be expressed as 1 over 2 pi, the integral of capital X of j omega e j omega t d omega. So this can be regarded as some sort of anti-transform formula or as the Fourier representation. So we are representing x of t as a linear combination of complex exponentials at different frequencies omega. Unlike the Fourier series, where there was a finite, discrete number of frequencies, here everything is a continuum. So that's why we have an integral. The reason for this is that the signal we're trying to represent is not periodic. And what about capital X of j omega, which is the Fourier transform? The Fourier transform is an integral itself, and is the integral of x of t e minus j omega t dt. Does this always converge? So can we always use these formulas? Not always, but we can do that for a very broad class of signals. Simply speaking, we could say that if x of t has finite energy, meaning that the square magnitude of x of t is integrable, so that the integral of the square magnitude of x of t is a finite quantity, then we can define a Fourier transform for x of t, and we can represent x of t as a linear combination of complex exponentials at different frequencies. Let's see a few examples where we'll take commonly used signals and we'll calculate their respective Fourier transforms by using the formula we just obtained. The first example we're going to see is a right-sided exponential function. So x of t is e and minus at u of t, where a is a positive number. So this is an exponential which is only right-sided because of u of t, the Heaviside function. This exponential only starts at t equals 0. Okay, let's calculate its Fourier transform with the formula. So by applying the formula, we have that x of j omega is the integral of our signal e minus at u of t times e minus j omega t dt. Of course, because of the presence of the Heaviside function, this integral effectively runs between 0 and plus infinity. Okay? We therefore get to a very simple integral which we know how to solve. And the result of the integral, after a couple of steps, is 1 over a plus j omega. So what does this function look like? It's a complex function, so if we want to represent it, one way is to represent separately its magnitude and its phase. Let's do that. So to represent the magnitude conveniently, one way I like to apply is I multiply numerator and denominator, in this case, by the complex conjugate of the denominator. Then I obtain what you can see on this slide, that the magnitude is 1 over square root of a squared plus omega squared. What does this look like? Well, you have a picture that depicts the trend of such function. So it's a function that has a sort of a bell shape, say. For omega equals 0, its value is 1 over a. And then it descends as omega grows for positive and negative frequencies. In particular, when omega is equal to a, the peak value has decreased by a factor 1 over square root of 2. What about the phase? The phase can be easily obtained, and it's minus arctangent of omega over a. And what about the trend of this phase? You see this represented at the bottom right of the slide. If we want to draw this intuitively without using any software, one way to do that is to observe the form of x of j omega, which again is 1 over a plus j omega, and think in these terms. So if my omega is 0, then I have a real number, 1 over a, so the phase is 0. If omega grows to plus infinity, then what I have is 1 over j infinity, we could think. So it's a purely imaginary number with a negative imaginary part, because j is at the denominator. Such number has a phase minus half pi. Conversely, when omega goes to minus infinity, I'll have a purely imaginary number with a positive imaginary part. That's why the phase goes to half pi for omega going to negative infinity. This way, I can already sketch the drawing you see on the slide at the bottom right. Let's see another simple example, but very useful and very insightful, the unit impulse or the Dirac impulse. So if your signal is delta of t, what's the Fourier transform? We use the formula here again, and the Fourier transform is the integral of delta of t e minus j omega t dt. Now this integral is extremely simple to calculate if you recall the property reported at the bottom of this slide. So when you multiply an impulse by a certain signal, what you obtain is the same impulse scaled by the value of the signal where the impulse is placed. So to say this in formula, delta of t minus t0 x of t gives you delta of t minus t0 x of t0. So the same impulse centered at t0 scaled by the value of the signal x evaluated at t0. So if we apply this to our case, well, we have the delta of t e minus j omega t will be equal to delta of t times e minus j omega 0, which is 1. So in other words, the result of the integral is 1 because it's just the area of the delta. Okay, what does that mean in practice? It means that the Fourier transform x of j omega has equal contributions, unitary, at all frequencies. Let's see another example, this time the rectangular pulse x of t. So this pulse is 1 between minus t1 and t1, as you can see in the figure, and it's 0 elsewhere. Let's calculate the Fourier transform. Again, with the definition, we have that the integral, which originally is between minus infinity and infinity, simply reduces to an integral between minus t1 and t1, because our signal x of t is 0 elsewhere. This simple integral can be calculated similarly to other integrals we've seen before, and the result can be written in a compact way as 2 sine of omega t1 over omega. There's yet a more compact way of writing this. Notice that this function sine of omega over omega is a very interesting function, because when omega is 0, it takes the form 0 over 0. Let's see how to represent this. Typically, one defines the sinc function as the sine of pi theta over pi theta. That is denoted as the sinc of theta. Okay, if we use this definition, then we can simply rewrite our Fourier transform x of j omega in terms of the sinc function. It would be 2t1 sinc of omega t1 over pi. We need to undergo a few tedious manipulations, but nothing difficult. The interesting thing is to observe the shape of such function, which is given at the bottom right of this slide. So the sinc function has a peak for omega equals 0. In our case, the peak is 2t1. And then it presents some oscillations. And the oscillations are attenuated, so they decay in amplitude. They're also equally spaced. So let's notice that the first 0, so the first crossing of the x-axis, or the omega axis in this case, occurs for pi over t1. The next crossing would be for 2 pi over t1. So all of them for integer multiples of that quantity. Let's look at another example which will seize the dual of the previous one. So in this case, I'm not giving you a signal in time domain, and I'm not asking you to calculate its Fourier transform. I'm rather giving you the Fourier transform, which has a rectangular shape, so it's 1 between minus w and 0 elsewhere, and I would like to calculate the signal that corresponds to this transform. So it's going to be an anti-transformation this time, but we know the formula for that, so let's do it. So the signal x of t that corresponds to such Fourier transform is a sinc function. How do we do that? We apply the formula for the anti-transform. So we have 1 over pi, the integral, which would be between minus infinity and infinity of a capital X. But in this case, capital X only extends between minus w and w, has a finite support. So that restricts the integration, and after a few calculations, we get that x of t can be expressed in terms of a sinc function again. So to be precise, it's w over pi sinc of wt over pi. Okay, and we represent this at the bottom right of the slide. So what's interesting here? There's a special relationship that has become apparent between a function or a signal and its Fourier transform. So in the previous example, we saw that a rectangular pulse in the time domain has a sinc as a Fourier transform in the frequency domain. And now we just saw that a sinc in the time domain has a rectangular pulse as a Fourier transform in the frequency domain. This is a direct consequence of the duality property for Fourier transforms. We will discuss this in more detail later on in the course. Now let's gain some insights into another important property of the Fourier transform by recalling the last example and just redrawing it for two different values of w. In this slide, w1 and w2. So the figures on the left have a larger value of w. So w1 is larger than w2. The ones on the right have a smaller value of w. We notice that as w increases, the Fourier transform x of j omega at the bottom becomes broader. On the other hand, the main peak of the signal in time domain becomes higher, and the width of the first lobe becomes narrower, right? What would happen if w went to infinity, if we made w larger and larger? Well, the signal x of t in time domain would tend to a Dirac impulse, narrower and narrower. All the energy would be concentrated in one point for t equals 0. The signal would be 0 elsewhere. What about the Fourier transform? The Fourier transform, represented at the bottom, for a W that goes to infinity would converge to a constant 1 that extends to all frequencies from minus infinity to plus infinity. Recall that we have already seen this in a previous example today when we calculated the Fourier transform of the Dirac delta, right? The transform of the Dirac delta is 1, it's constant. Cool. So in summary, the behavior shown in this slide is an example of the inverse relationship that exists between time and frequency domains. So broadening a signal makes its Fourier transform narrower, and vice versa. That's all for this class on the Fourier transform of aperiodic signals. In the next class, we'll learn how to calculate the Fourier transform of periodic signals. In that case, we won't be able to use the formulas we obtained today, as those formulas only apply to finite energy signals and periodic signals have infinite energy. But we will have to find another way. See you in the next class.